Hello friends, we will start with a new module today on crystallographic texture. Okay. So, the idea here is to make you understand the crystallographic texture, and suppose if you see it anywhere, you should not be leaving it, that maybe you are not able to understand it completely. Okay. So, it will not be a very exhaustive course on how to do the texture analysis. Okay. The idea here is just to make you acquaint with the crystallographic texture, so that if you see a particular representation of texture, you should be able to understand and you should be able to correlate with the mechanical properties, if there are any mechanical properties or any other properties are related with the texture. So, you should be able to understand that what the author is trying to convey. Okay. So, in that actually the first basic of the understanding starts from the stereographic projection. So, that is what I am taking today as the first lecture in this particular module. So, basically texture, just a quick way to show you that what do we mean by texture is basically if you see a individual grain in a polycrystalline material. Okay. So, what is the identity of the grain is that how the unit cell is oriented in the grain. Okay. For example, in one grain the unit cell is like this. Okay. In another grain the unit cell may be like this, in another grain the unit cell may be like this. Okay. So, if suppose all the grains are random, all these unit cells in individual grain are randomly oriented, then we would call it as a weak texture or random texture. Okay. There is no particular way the unit cells are arranged in individual grain. Okay. But if you find that some of the grain or a good number of grains, okay, have a particular orientation of unit cell, okay, and these are not required to be together. Okay. These grains spatially can be anywhere throughout the material, but if we find that, let us say out of 100 grains, suppose 30 grains have a particular orientation, for example like this, okay, then I would call that the material has a certain texture, okay, crystallographic texture, that there is a preference for a certain type of arrangement. Okay. So, that is what is shown here in the schematic here. Okay. As you can see in this first instance here, all the unit cells are arranged in a particular fashion. Okay. So, I would call, because in this case all the unit cells are arranged in particular fashion, I would call that it is highly textured. Okay. Whereas, in this case, the second case here, you can see that all the unit cells are randomly oriented, all have different orientation. So, I would be calling maybe it has a random texture. Okay. There is no particular preference. Okay. And usually when we have to define a unit cell that is in 3 dimension, okay, if I want to define that what is the orientation of this unit cell, okay, I have to have some reference from which I can take, or I can tell you that what is the orientation of this. Okay. If there is no reference in the space, I cannot define that what is the orientation of this unit cell. Okay. So, to define a reference frame which I can use to define the orientation of this unit cell, okay, usually the most popular one, because rolling is one of the most popular processing technique, okay, the symmetry is taken from there, okay, and it has a orthogonal symmetry. As you can see, you have rolling direction. Okay. So, this is your rolling direction, for example, this is your transverse direction, so T d, okay, and this is your normal direction N d, okay, all perpendicular to each other. Okay. So, this is a reference frame which I can use to define the orientation of the unit cell. How we are going to do that, we will see. Okay. So, if in terms of texture representation, we will come back to this again. Okay. Basically, you have 3 methods, either you can show it in terms of pole figure, okay, or you can tell it terms of HKL UVW, okay, or you can tell it in terms of what we call as orientation distribution function method. Okay. For example, this HKL value, the example is shown here, okay, as we have already seen that my rolling direction, transverse and ND are the reference frame. Okay. So, basically we are trying to say that which HKL plane of the grain is parallel to the, suppose this is my rolled sheet, okay, this is my rolling plane. Okay. So, which plane of this unit cell is parallel to the rolling plane. So, suppose if I keep the unit cell like this, I can say my 001 plane is parallel to the rolling plane, and then I can say that which direction is parallel to the rolling direction. Okay. So, if you see my direction is either 100 or 010 is parallel to the rolling direction. If I put unit cell like this, then 110 direction will be parallel to rolling direction. So, I can use this HKL UVW method also to express that what will be the orientation of the unit cell. Okay. But before going further, because pole figure is one of the most used and important way of representing texture. Okay. So, before coming to pole figure, I will first introduce you to the stereographic projection, because using stereographic projection only we can go to the pole figure, how to create pole figure for a particular orientation. Okay. So, what is stereographic projection? So, it is a very convenient way to depict any 3-dimensional information. Okay. So, as you can see that when I am talking about a unit cell, okay, I am talking about a 3-dimensional information. Okay. You have different planes in 3 dimension, okay. You have different directions, okay. Some plane can be at angle like that, but I cannot do any analysis in 3 dimension like that. So, I have to depict all this information on 2 dimensions. Okay. And when we are discussing about crystallography, okay, our main purpose is about what are the angles between the different planes. Okay. I am not concerned with the dimension of the plane, because it can be of infinite size, still it has no particular meaning for us. Okay. But what are the angles between different planes and direction, that is of importance to us. So, when we are doing this projection, we want to preserve the angular information. So, angular information should not be distorted. Okay. So, when we are doing this projection, we are preserving the angular relationship. Now, continuing with stereographic projection, basically every plane is defined by its normal. Okay. And these normals of different planes, okay, are starting from one we call as sphere. I will tell you that what do we mean by this reference sphere. Okay. Actually, we are saying that all the normals to the planes are starting from the center of a reference sphere. Okay. And what these normals are doing, they are intersecting the surface of reference sphere in a set of points which are called poles. Okay. Just bear with me, I will explain all these things to you in an animation right now. Okay. So, basically if I take a unit cell like this, so you have a plane, okay, there is a normal. Okay. So, this normal will go and cut a sphere. Okay. We will I will discuss what a sphere means, and then we project these poles on a projection plane in such a way that we preserve the angles. Okay. And the poles represent the orientation of the planes, orientation of crystal by their position on the reference sphere, and plane may also be represented by its trace on reference sphere, making a great circle on the reference sphere. Okay. So, just quickly I will show you what do we mean by this. Okay. So, basically this is the idea of stereographic projection. You can take a unit cell like this. Okay. Take a very tiny unit cell, okay, very tiny. So, that the idea is that all the normals from the plane, okay, should be seen as they are coming out from the center of the sphere. Okay. And what is the sphere? A sphere is an imaginary sphere around this particular unit cell. This unit cell is at the center of the sphere, and in imaginary sphere you can take a sphere as big as you want, maybe equal to the size of the universe if you like, okay, it does not matter. Okay. And then we are looking at the normals which are coming out of these planes, okay, and where they are cutting this sphere. Okay. So, wherever they are cutting the sphere, okay, that will be called as pole. Okay. And if I extend this particular plane, okay, instead of taking normal, if I just extend this plane will also go and cut the sphere at some place. Okay. So, that will be called as the trace of the plane. So, you have, for every plane in the stereographic projection you have a trace, okay, and you have a pole. Okay. But still it is still in 3 dimension till now. Okay. We have to bring it to 2 dimension, that is where the projection will come. Okay. So, I will explain that with a animation here. So, basically you have a unit cell like this, then I am taking it a very tiny unit cell, okay, and there is a sphere around the unit cell, and I am taking a plane which is cutting the center of the sphere, okay, which is passing through the center of the sphere, okay, and this plane I am calling it as a equatorial plane for which is dividing this sphere into 2 equal parts, 2 hemispheres basically, and let us call one as top hemisphere, another as bottom hemisphere, okay, basically 2 poles. Okay. And then I am taking the normals. Okay. So, in this case I am interested in 100 planes. Okay. So, I am taking the normals of 100. Okay. So, one normal as you can see is coming out from this particular plane here, okay, and hitting cutting the sphere at some point. So, this is the pole of this particular plane. So, if I call this plane as P1, so this is the pole of P1, okay. Let us say call it as PP1. Then there is another normal going from another plane, okay, another 100 type of plane, okay. Then there is a third normal which is also coming out of another 100 type of plane, okay. So, let us call this as P2 and this as PP2 and this as P3 and PP3, okay, this particular plane is P3. So, you can see that I have taken 3 normals here from 3 different planes. I can take from other planes also, just for simplicity I am taking it from 3 100 type of planes. Okay. There will be also normals to 100 plane which will go in the southern hemisphere like this, okay. But I am not interested in the normal which are going in the southern hemisphere, okay, or the bottom hemisphere. I am only interested in the normal which are going in the top hemisphere, okay. And I am also kind of creating a reference frame on this plane, equatorial plane, okay, and that I am calling as north, south and east, west, okay. So, right now it is in 3 dimension. When we will see from the top, okay, then the north, all these 4 will be projected on the screen. So, now still it is in 3 dimension, all the information. So, now I am taking connecting this pole with the pole of the bottom hemisphere, okay. All the and when I am doing this projection, this particular projection is this particular pole is projected on the equatorial plane like this. Similarly, I will join this pole with the bottom hemisphere pole, okay. It is also cutting the equatorial plane at this point, okay. So, there are 2 already, then the third one projection, this will also cut the equatorial plane in the at one point. So, basically now 3 dimensional information we have reduced into 2 dimension, okay, by these poles, projection of poles, okay. So, now I am just changing the view here, okay. Now, I will start seeing from the top, okay. So, from here I will see that what is the condition of different projections, okay. So, when I am doing that, I am changing the view here, okay, Now I am looking from the top, so T should come somewhere here at the center, okay. And as I told you, north south I have plotted there. So, north will come here, south will come here, east will come here, and west will come here, okay. So, I have removed the other part of the equatorial plane. I am only taking the trace of the equatorial plane, which was cutting the sphere, okay. So, this is my trace, okay, of the equatorial plane, okay. So, this is my north, south, east, west, okay. So, these 3 points, the normals which we projected will look something like this, okay. So, only 1 0 0 poles we were taking, okay. Those 3 poles are projected here. The other 3 poles will be in the bottom hemisphere, that we are not projecting here, okay, because then it will be more confusing to do analysis, and because of symmetry it does not make any difference. So, only we are projecting the top part of the hemisphere, okay, and these 3 are the projected poles on the equatorial plane, okay. Now, just to give you a more understanding of this, okay. So, as I told you that we started with the unit cell, okay, and suppose this unit cell is at the center of this particular sphere, okay. So, suppose it is oriented something like this, okay. So, this one pole will go maybe hit somewhere here, okay. This one will go and hit somewhere here, okay, and let us take slightly here. So, the third one may be hit somewhere here, okay, and then we are taking projection on the this particular plane here, which is going through this, and that is projected, okay. If I want to find the trace of these planes, suppose this particular plane for which this is the pole, okay. So, this plane will be extended like this, okay. So, if I want to take the projection of this plane, okay, it will be the plane on the reference sphere will be something like this, okay. And these trace will also be projected on the equatorial plane, okay. So, on the equatorial plane, okay, how it will look like, I am just showing you in this particular slide here, okay. So, this is a plane, okay, for which this is my pole P1, okay, and this is the plane which is extended, and when it is cutting the sphere it will form a projection like this, okay. This is another plane for which this is the pole P2, and this is the another trace for that, okay, pole, and then this is the angle between the two P1 and P2. I will show you how to find this angle between two planes, okay. So, right now it is an angle on another circle, okay, where we are finding the angle between these two pole, okay. So, this is how you can find pole and trace of the plane, okay. So, when you have this kind of stereographic projection, okay, we define 2 types of circle, okay, and this is very close to what you see on the atlas, okay, that you have some what we call as great circles, and these circles are the one for which the center coincide with the center of the reference sphere, and some are small circle for which the center does not coincide with the center of the reference sphere, okay. And as you can see, all these are actually great circle, okay, this one, because their center and the center of the sphere are same, okay. So, all the angular measurements actually we do on the great circle, okay. I will show you that how we can do that in the next lecture, okay. First, let us see that how this particular the circular projection can be divided into multiple circles. For example, this is right now a 3-dimensional globe kind of sphere, okay, and you can see that it is divided into different by different longitudes and latitudes, okay. So, all the longitudes are the great circles, okay. So, all these longitudes are great circle, because their center and the center of the sphere are same. Whereas, all these latitudes are small circles, their center will be somewhere here, which is not going to match with the center of the sphere. Only one latitude is such that its center matches with the center of the sphere, and that is what we call as equator. Okay. So, very similar to what you see in the atlas. Okay. So, this is a typical, so all this basically traces also which we have plotted, that can also be projected on the equatorial plane. Okay. So, if you do that, they will form this kind of great circles. Okay. So, that you can do a graduation here, okay. You can do a marking, and that is how you can get a construction which we call as wolf net. Okay. So, this wolf net we are going to use for doing all our calculation for the stereographic projection. Okay. So, it has north, south, east, west and so on, and this particular one is graduated with 10 degree interval. Okay. So, every 2 graduations have a distance of 10 degree. Okay. And when you completely do these projections, okay, basically what you can get at the end of it is a standard stereographic projection. Okay. So, what does it mean? For example, in this particular case, we are saying that it is a standard 001 stereographic projection of cubic crystal. Okay. So, when I am saying standard 001 stereographic projection, I am putting keeping the unit cell like this. Okay. At the center of the sphere. So, what will happen? The 001 will go and hit directly the top pole, okay, and it will be projected exactly at the center, because whatever is hitting right there, and when I am connecting it to the bottom pole, okay, that will go through the center of the sphere itself. Okay. So, that will be obviously coming at the center, okay, and that will be 001. Now, you can see that other normals, suppose this is your 100 plane and this is your 010 plane, the green is 100 plane. So, 100 will go and it is going through the equator, in the equator itself, okay, and hitting the sphere at the end. Okay. And when I take the projection from there, the projection will be exactly at the equatorial plane itself. Similarly, 010 will go like this and hit the sphere, and if I take the projection of that, it will be directly at that particular location itself. Okay. So, you can see these two conditions here very nicely. So, you have 100 at the one end and you have 010 at the another end, and there is a 90 degree relationship between the two. Okay. The other poles I am not showing right now, because in the next lecture we will see that how I can use this stereographic projection, okay, to plot a standard stereographic projection like what you are seeing here. Okay. So, basically what you are seeing here is that all the poles are, or all the planes are plotted on a 2 dimension and their angular relationship is preserved, okay, and you can easily see that what will be the using wolf net, what will be the angle between different planes. Okay. So, all the poles like 011 type, okay, will be plotted here. Okay. You can see all these poles of 100 type, 110 type, then you have all the poles of 11 type. These are the important planes for us. Okay. So, all these are plotted on a stereographic projection. Okay. So, in the next lecture I will show you that how I can use the wolf net how I can use this stereographic projection to draw a standard stereographic projection of a particular orientation of the unit cell. Okay. And that once we understand that will help us in creating a pole figure for a particular orientation of the unit cell. Okay. So, I hope this is actually some kind of imagination is required in 3 dimension. Okay. So, I hope you might have able to understand that how I can plot a standard stereographic projection, how I can do a stereographic projection plotting. Okay. And now, I will tell you how you can use this to create the standard stereographic projections. Okay. Thank you.